This video is about transition state stabilisation and why is it important. I'm going to start off with 3 graphs. Let's roughly do it like this. So this is to do with enzyme and biocatalysis. So we've got the Gibbs free energy and the reaction coordination. Yeah, so G, delta G, R, C. If we have no enzyme, then it's going to be a standard reaction profile. So this point here, this here, we can say this is the minimum. No, this is the maximum here. And this energy is the transition state. Because here, we can, there's a transition state from when, so for example in SN2, this would be where the coordination, where there's an inversion of stereochemistry, so it flips. The point where it transitions to the next part of the reaction. So we've got the substrate and the products here. So that's the energy required. If we use an enzyme, so this is no enzyme. If we use an enzyme that's complementary to the substrate, so it fits around the substrate, so complementary to substrate, then you'll get something that goes like this. So you see the normal path is through here. Again, this is the transition state. And what transition state stabilisation is for example, let's say you have a system that does intermolecular hydrogen bonding. When the tertiary intermediate is made, so let's say you've got, can we see that? Yeah. We've got an O minus, so this has been made from a double bond, it's been broken. This could be stabilised by surrounding molecules, so this is important for the chymotrypsin digestion catalyst, as this stabilisation will make it happen a lot faster than it does in reality. Coming back here, got this, so we see that it's complementary to the substrate, so that means the enzyme holds it tighter, but it means you have to put more energy into it to get to that transition state, and I'll draw some diagrams after this. So it comes down here. This reaction is where the enzyme is complementary to the transition state. So if we draw it, right, so we see the Gibbs free energy is even less, and the uncatalyzed version will go up here. So we need to think, well, why is this the case? If it's complementary to the transition state, what does this actually mean? So I'll give you the example that we were taught, which is you have a stick. Let's say that's the substrate or the reactant. S for stick, yeah, the substrate. The transition state is almost like you bend the stick. So this is, your hands are on it and it's bending, and then when it breaks, that's the actual product. Yeah. That's the product. So if you've got an enzyme that's complementary to the substrate, this means that, so this is the substrate. The way the book spoke about it is, it's like magnets. So it surrounds it, and it's going to be hard to bend it because all of these magnets are holding it together. So this needs to eventually go like this, right, to support the transition state. And that's going to require more energy to bend that. Whereas in this case, where the enzyme is complementary to the transition state, this means it already starts off like this. So, oh, excuse me, that's the substrate. So then when you actually get to the next step, it's already bent. So this is the transition state, it's stabilised. So less energy. Do you see that this system supports it, the magnets, if you will, as we suggested here, the intermolecular hydrogen bonding from other systems stabilise it and hold it there for longer. That is that.